All right, so we're gonna pick up right where we left off yesterday, and let's do a little bit of review. So if you're looking on the screen, I'm gonna go back here, and I put a link. If you scroll up in the chat, I put a link to the step-by-step instructions, and that's a PDF file you can download, and it's a good 5 or 6 pages long. And we got all the way through to, we got past the project tab. So it kind of follows these tabs across the top here, project, libraries, floor plan. So you click on project and it kind of walks you through everything that you need to do here. We talked about, checking your conditioned floor area against the volume as you draw it. And then we talked about the libraries. This is where all the different types of assemblies are stored, so you can change them quickly later on. You can edit these, and I don't know if I remember mentioning it last night, but you can also export these. So if you create a whole bunch of new walls and you want to use those in a different project, you can export them to a folder, and then you open up a new project, and then you can import them into that new project, okay? So that's a nice feature to be able to keep track of all this stuff. So we got window types, wall types, doors, floors, ceilings, rooms, roofs, and ducts. So those are all different things where at some point in the software, you're asked to pick a type of those. And so this is where you store all those types, so you don't have to change them over and over again. Then we went to the floor plan tab. This is where you import your floor plan, which down here, let me turn off some of these things so you can see it. So this floor plan down here of this really simple little house, it's a 20 by 30, really simple house. And this drawing that you see laying on this green background is the floor plan. So I imported that, and you can import any image file. So a PNG file, a JPEG file, all those different kinds of image files. You can also import a PDF file. Now you have to be careful because a lot of times people will ask for a copy of a set of plans from somebody, and they'll send you a multi-page PDF file. And it'll have, the plot plan, the floor plans, the elevations, the roof plans, all these other pages and pages. And if you can import that and put it in here, the problem is that's a gigantic file. And when you start, manipulating in 3D, like I'm doing now on the screen, the software has to rotate that entire file, and it gets really, really cumbersome, and it uses up a lot of CPU power. And so the best way that I have found to do it, to get a nice clean file, and you also know if you look at architectural plans, if there's on a floor plan like this, there's usually all kinds of notes and clutter and all kinds of stuff around the outside, and I really like to trim all that off. So what I typically do is I'll just open up a set of plans in a PDF viewer. I'll zoom in on just the part that I want to see, and then I'll take a screen snip of that using the Microsoft Windows snipper tool. And then when you take a snip, it saves it as a PNG file, and then I just open that PNG file. And that's what I did here. It just makes a nice, clean, efficient little file that's easy to manipulate, and it works a lot better, okay? So we talked about all the floor plan stuff, and then we went to rooms, and we placed all the rooms.
Can you show them, because people were asking how the importing and exporting works on the libraries?
On the libraries? Yeah. So I'm going to go to the libraries, and if you look down here, you've got copy, delete, so that edits this little table. But once you get your table all the way you want it, you hit export. And I don't know if you'll see what I'm able to see.
It's not working on this?
I don't know, it may not work because of the viewer. It wants to open a different window or something. Well, anyway, yeah, you click this export button, and it opens up a little, little file viewer window, and it'll ask you where you want to save it, and it just saves them. And then when you go in and open another project, you hit import, and you go and browse, and you find that file, and you import.
Oh,
that
you have
in.
to select one of them.
Like that?
Yeah, and then hit export.
Okay. let me go to walls. That makes more sense. So I'll pick this first wall here, and then I'll hit export. Oh, there it goes. And so it's saving this. So you'll tell it where you want to. So you'll probably create a folder of libraries, okay? And so it's saving that wall. And so you can create this gigantic folder, which sort of becomes your real library, your sort of outside library. And I'll just save it there. And then when you go to a new project, there it is right there.
And you can hold shift here and select multiple of them if you want.
Okay.
And then you can hit open.
So what's a KEWLT file?
So it's quick energy wall type.
Okay. So you can save it by walls, you can save it by floors and stuff like that. So basically each individual row here can be saved as a little file. Okay, and then you can do that for all your walls, all your floors, and all that other stuff. So I accidentally created an extra one here. We'll delete that.
And if you hit export all, it's like you selected every single one of them, and then.
Oh yeah. So this export all here would do the whole table all at once. The export all button. Okay. All right. So we got to rooms, and yesterday we showed you how to manipulate rooms and draw them and save them as different types. So over here you got your different room types. So most of your rooms will just be conditioned rooms. You can save it as an unconditioned room like a garage. And we have this one here called Earth. And Earth is if you're going to do a basement and you want to show that a wall is a below grade wall, what you do is you draw a box next to it like this, and you drag it out, you highlight that box, and then you call it Earth, and it turns it brown. Okay. So now what it's telling the software is that this wall right here between this space and this Earth is a below grade wall. And so that's just how you designate stuff as below grade. Because you could have, like a walkout basement where, let's see, do this right here. So turn that into Earth. So that would be kind of like a walkout basement where you've got, your Earth is slanted against the house. So this wall here is above grade, but everything over here is below grade. I don't have it quite all the way down, but so you can do stuff like that. It'll treat that wall differently as a below grade wall. That's something Manual J needs to know. All right. And then let's see if there's anything else I forgot to talk about yesterday. I talked about grouping and ungrouping. This is all your different kinds of boxes that you could create. Well, let me show you real quick how to do a bay window, for example. Okay, I don't have one on the plans, but bay windows are pretty common. And so what you would do for a bay window is you start off with a rectangle like this, and then you take a triangle room, tab rotates it, tuck it back in that corner like that. Put another one over here, then we down from the top. By the way, I mentioned this yesterday, but when you think like that, it just means that they're overlapping and you have to pull them apart a little bit so they're not overlapping like that. Okay, so there, that would be like a bay window. So you just make it out of, there's pretty much any possible shape of a room you can imagine, you can build it out of the blocks, the different shaped boxes that we have. And then of course, don't forget, you're going to want to group those all together by highlighting one, and then you hit Shift, click them all, come over here and hit Group, and then they all, oops, I did something wrong. Group. What are they grouping? Is it because they're not conditioned?
Yeah, you can, wait, are they all in condition? Click on the other ones. Yeah, now you can group them. Yeah, they have to be the same conditioning.
They have to be the same type of room, that's why. I was trying to group conditioned rooms with unconditioned rooms, and it wasn't letting me. It's smarter than I am. All right, so once you group them, they become one individual unit, and they'll move together like that. And when it does the load calculations, it assumes that's one room. And so that shows up in the table as one single room.
Dog is asking if we can make round cylinders yet.
Dov, no round cylinders. You have to make a whole bunch of little tiny triangles. Sorry. Yeah, when you do a load calc on a lighthouse, let us know. We'll help you figure that out. All right. So that was rooms. Then we talked about windows, putting the windows in here, and you know, the whole reason we're doing all this is because we are going to have Manual J tabulate all the heat transfer through all of these surfaces, okay? So our goal is to size a heater and an air conditioner to offset the heat transfer coming into the house in the summertime and leaving the house in the wintertime. And if you came to the introductory class that we did a month or so ago, I had the example of how a house is like a tank of water. And, you know, the water was escaping in 3 ways, and we had to size a pump to replace the water, and we had to calculate how much water was leaking out, how much water was seeping out, how much water was evaporating, so that we could size our pump. Well, that's an analogy of doing a load calc to size a furnace. And instead of water, it's BTUs are escaping from the house. And BTUs are leaving the house through the walls, okay? That's conduction through the walls. It's escaping by conduction through the windows, the ceilings, it's escaping by infiltration, and a little bit of radiation, but Manual J doesn't count radiation for heat loss. But for heat gain, that's the heat coming into the house, and we need to know how fast that heat is coming in so that we can properly size an air conditioner to extract that heat at least the same rate. Because if the heat's coming in faster than the air conditioner can get it back out, the heat builds up and builds up and builds up, and the house gets hotter and hotter and hotter. So you need to size your air conditioners. That's the whole purpose of Manual J, or those 2 calculations, is how fast in BTUs per hour is the heat coming into the house in the summertime, and how fast in BTUs per hour is the heat leaving the house in the wintertime. And you can do that on what we call a block load, which is the entire house all at once, and that will allow you to size your furnace and your air conditioner. But we need more information than that because we need to also size ductwork. And so instead of doing a block load for the entire house, we're going to do room by room loads. And instead of calculating that BTUs per hour for the entire house, it's going to separate it into rooms. And so when we build our house, we're going to separate it into rooms. And so, let's see, this room is going to have a certain heat calculation, okay? Now, when I pull it out like this, it's got 4 walls that has heat transfer through it. But when I slide it back into place, the only exposed or exterior wall that it has is this front wall here and this window, and then the side wall here that's going to an unconditioned garage. This back wall back here, there's no heat transfer through there because that's another conditioned space on the other side. And Manual J assumes that the entire house is the same temperature. And when you have the same temperature on either side of a wall, there's no heat transfer through it. Okay? It's called an adiabatic surface. And so we don't worry about these interior walls or these interior doors, but we do need to know that this ceiling is associated with this room, this wall, and this window, and then this floor. And so it's going to calculate the BTUs coming in the summertime and the BTUs leaving in the wintertime for just that room. And then we're going to do that for each and every room. We're going to add those all together. We're going to use that total to size our equipment. And then by knowing the room by room loads, we can distribute the air proportional to that room's load. In other words, if this furnace is going to give us a certain amount of air, and we need to know how much air is going to this room so that we can size the duct, it's a percentage. What percent of that room does it account for the total load? That's how much air we're going to give it. The air delivery in terms of percentage is proportional to the room's load relative to the entire load. In other words, if this room is 10% of the total load, it needs 10% of the airflow, okay? So we size our furnace to meet our heating load. We size our air conditioner to meet our cooling load. Once we pick that equipment, it will tell us how much airflow we have to work with, okay? And then it'll, there's some other things having to do with static pressure and stuff like that, but it'll tell us how much airflow we have to work with. And then the software will know those percentages. It'll know those percentages, and it will divide that airflow up for us and say, okay, this room needs this many CFM, that room needs this many CFM, and so on and so forth, okay? Now, the other thing I didn't talk too much about yesterday was this harmless looking little circle. Connor, make it so I can see what they're seeing, please. This harmless little white circle down here, okay, called a north arrow. And if you're doing cooling load calcs, that's a very, very important little thing, because the direction of a window has a huge impact on how much heat is coming in through that window in the form of solar gains. So right now, this house is facing south. The north arrow is pointed up. This is the front of the house. So the house is facing south. So you can kind of imagine the sun is going to be rising on the right-hand side, passing overhead, if you can follow my cursor, and then setting to the left side of the screen, coming almost straight overhead in the summertime. And so these windows aren't going to get a whole lot of direct sunlight in the middle of summer because the sun's going to be kind of straight overhead. But this window over here on the west, as the sun is setting in the afternoon, it's going to get some light just pouring through it. It's beating through that room. It's going to get hot because of that one little window there in the afternoon, okay? And on the back of the house, these all face north. They're rarely going to get any direct sunlight, okay? So, and then here, look at the skylight we put up here. The skylight is facing west, so that the heat's really going to come screaming through that skylight there, okay? So direction's very important, and that's why overhangs are important for south-facing windows like this, because if the sun is passing directly overhead, all it takes is a little tiny overhang to completely shade that window. Whereas on the west side of the house, you could have a big overhang here, and the sun will still go down and come underneath that overhang on the west, okay? This house doesn't have any east-facing. And so it's very important that you know the direction that the house is facing and you have your north arrow pointed accordingly. And if we have time, I can do a load calc, and then I can come back and move this north arrow. So now these windows all face west, redo the load calc, and you'll see there's a pretty substantial difference, okay? I used to teach a 3-day manual J class. In fact, I used to teach it down at Steve's place in Tulare there at the Southern California Edison Training Center in Tulare. We had a 3-day active manual JS&D class, and one of the example houses, if I remember right, it's about a 2,500 square foot house, and when it was facing one direction, it was a 2.5 ton air conditioner, and when you rotated it 90 degrees, you take the exact same house and you rotate it 90 degrees, it went to a 4-ton air conditioner just because of the rotation. Now, it was kind of an exceptional house because it had a whole lot of glass loaded up on one side, and it had overhangs on some windows. But it just illustrates the point of how important orientation is, okay? And if you go into Manual J, which is where all the calculations are coming from, and you look at the tables, look at the table for the windows, for the heat transfer multipliers for cooling, and you just look at a window and look how dramatically those numbers change. They double and triple and quadruple just as you go from, east, west, north, south, and across the table like that. So that really illustrates how big of an impact it has, okay? So make sure that your north arrow is correct. And on our step-by-step instructions, that we're going on, that's one of the things that'll remind you to do. Okay. So we did all that. We placed, let's see, I went to the data table here. And so the data table is where everything is, where everything's tabulated. It's where all the tables are, okay? So we have one system in here, FAU1. We've got a bunch of rooms. And remember, we came in and we named those rooms. If the house has more than one system, you have to say which system that room is being served by. And so if you had more than one system, this little drop-down list here will give you more than one choice, okay? And let's see, we got a floor area, we did the room types, and then we distribute our number of occupants. Remember, number of bedrooms plus one, and then just distribute them where you think it's reasonable for those people to be when the air conditioner is running, basically, okay? All right, we did all that. Let's see, we went through, we checked all our walls. We just kind of get this where we can see it. Highlight the first wall, and then I'm just going to scroll down so you can look at all those different walls. Remember, we had to go in and indicate that this wall and this wall, that these two walls right here were knee walls. That was a different type of wall, so we had to go in and pick knee wall so that Manual J is doing the right kind of load calculation on that. Knee walls have a bit more heat transfer through them than a regular exterior wall, because what a knee wall is you've got house on one side, so you've got conditioned space. Let me see how we can actually get inside the house here. You go inside the house and you're looking up in the kitchen. So you look up, you see this wall up here. So if you're inside the house, you see this wall. Okay, it's up high. You're looking up a vaulted ceiling, it's up high. And if you were to drill a hole through that wall right there, it's going to come out in the attic on the other side where the furnace is over here. So that's considered a knee wall. A knee wall separates conditioned space from attic, okay? And knee walls, it's important to identify those correctly because they have a lot more heat transfer through those walls than, say, this wall over here, like this one here, that's between conditioned space and the outside. The reason is because the attic gets so much hotter in the summertime because of all the solar gains on the attic. So the delta T across this surface, because the attic is so much hotter, the delta T across the surface is higher than the delta T across this surface here. Okay, so that's why it's important to identify knee walls. One of my favorite stories about knee walls and interior walls like that was we did a design on a project in Las Vegas, and they had this exact situation. They had a vaulted ceiling like this in the living room. The bedrooms next to it were lower ceiling. And this was a subdivision where they were experimenting with metal studs. So the exterior walls were wood studs like a normal house, but all the interior walls were metal studs like in a commercial building. And in this wall right here, they had metal studs in this wall. And so the metal studs went all the way through this wall, and then they protruded up into the attic. And the back side of these metal studs were exposed to the attic. And if you can imagine attics in Las Vegas, they get pretty hot in Las Vegas, and the heat was heating up that metal stud, and you could actually feel it through the sheetrock down below. You could walk along this wall and find the studs with your bare hand because they were so hot. You just felt for hot spots in the wall, and it was because the attic was so hot and the heat was conducting down that metal stud, okay? Now, that kind of a heat transfer is not really well accounted for in Manual J. That's just not something they think about doing. You can model metal studs, but what it'll do is it'll only model this wall here as being a metal stud. It won't take into account the fact that all that metal is conducting down into this interior wall. That's actually something extra that is really not accounted for. What they should have done is put some sort of a thermal break across the bottom of this wall to prevent that heat from conducting down. So that was just kind of a weird situation, but it really illustrates the importance of modeling knee walls, okay? All right, so we got all that in. we got the data, and if you're following on the step-by-step instructions, we are on we got to step I, which is energy gauge loads, okay? Then we click this energy gauge loads button up here, and it asks you to confirm if you want to save it. It's always a good idea to save your project. And then, all right, so this is energy gauge, and you can tell because up here in the upper left corner, it says Energy Gauge USA with active manual J loads. And so we went through this yesterday. This is where you come in and you pick your city. So we picked Sacramento, California, and it sets all your temperatures for you. Then we go back and we defined our cooling system. So it's a central split system. We defined our heating system. It's a natural gas furnace. We also, specified our system name. When we define the system, we have to say this system belongs to this system block, and then that will show which rooms are in it. This is a one system house, so it's easy. Then we define our duct system, okay? And this is where you tell it what your duct R values are and the duct surface area. It will calculate a default surface area for you. That's usually good enough. It'll ask you where your ducts are located, where your air handler is located, and then it'll ask you about duct leakage. How are you defining duct leakage? In California, if you're installing a new system, the maximum allowed duct leakage, and this is tested in every house by a third-party inspector called a HERS rater, to be no more than 5%, okay? For existing homes that have been altered, if you're just replacing just the furnace or just the air conditioner, the maximum allowed leakage is 15%. So that would be a reasonable number to put there. If you're going to test it and you know otherwise, you can put in a different number. You can also define the leakage differently. You can define it as a percent of efficiency and things like that. So 5% is very common for California. So you'll need to kind of figure out what it is, what's best for your area if you're outside California. And then we said, okay, this duct system, it wants to know which heating and cooling system it belongs to. There's only one, so we just defined that. Okay. And then we did our mechanical ventilation system. In California, we have to follow the Ashrae 62.2 ventilation requirements, and the most common way that that's done by builders is to put in an exhaust fan. And there's a little calculation based on the square footage of the house and the number of bedrooms. And it'll say you need at least this many if it's going to run full time and all this other stuff. But there's also some really, really nice ERV and HRV systems out there where you'll have balanced ventilation. So the same air that's leaving, the same amount of air is coming in, and they go through a heat exchanger and they exchange heat with each other. So you're tempering the air that's coming into the house, and it doesn't use as much electric or cooling energy or whatever. And so you can define that as well. So you would have the CFM going out, the CFM coming in, what percent runtime, how many watts does it use, and then there's an efficiency number for ERVs and HRVs, and you can put that there. Okay, so you can certainly do that as well. Then once we got all that done, okay, we were ready to do, well, sorry, not quite. We defined our set points. 68 and 75 are standard for California. I think if you pick a different state, it'll actually say 70 and 75. And then you define how you want to do your infiltration. So you can use default, or you can define it as an air change per hour. And I have a handout that's on our downloads page that will give you the math for doing that, okay? So if you do, it's tough if you're building a house from a set of plans. If you're designing a house from a set of plans, you just have to guess, or you have to use good engineering judgment and talk to the builder and say, hey, are you going to build a really, really tight house, or are you just going to build an average house? And you have to try to narrow down, what you think it's going to be. And if you live in a humid climate, the infiltration has a huge impact on the load counts, okay? If you live in a dry climate, it can have a significant impact, but it's not quite as much because it doesn't contribute to the latent load quite as much. So this can be a very significant number. Now, if you're designing for an existing home, let's say it's an old home and they just want to completely reinstall a whole new system, tear out all the ducts and put in everything's new, and you want to design a new system for an existing house, That's actually better because then you can measure. You can, if you don't own a blower door, you can hire someone to come out and do a blower door test and measure the leakage, okay? And if the leakage is really, really bad, what you should do is tell the homeowner you should house up. I do not want to design. I have a personal philosophy. I refuse to design an HVAC system for a shitty house. Okay, I just refuse. It's against my basic philosophy of HVAC design to design an HVAC system for a really crappy house. So what that means is, it's just kind of a silly way of saying, fix the house. Instead of oversizing equipment for a crappy house, fix the house, seal the house up. You know, what if the house had broken windows? Do you do your load counts assuming a broken window? No, you fix the window. It's the same issue. If the house is really, really leaky, don't design for a really, really leaky house. That house is broken. Fix the house, seal it up, get it down to a reasonable number, and then do your load counts based on that. Okay, so that's just, I'll get off my soapbox. That's just my personal feeling about it, and that's how I like to teach it. All right, so we got to that. Let's just do default up here. And then if you're following in the step-by-step instructions, it says go ahead and click the button that says calculate active manual J8. Now what it's going to do, it's going to take all those windows, all those walls, all those ceilings, and it's going to go to a bunch of tables, and it's going to say, okay, it's this kind of a wall. I'm going to grab this number, and I'm going to multiply that times the area of the wall, and I'm going to get a heat transfer, and I'm going to tabulate that for all the rooms, and then I'm going to add them all up for the entire house, okay? And that actually happens surprisingly fast. I'm going to click this, and boom, there we go. The load counts are done. So we bring this down. So over here, winter building load, our total heat load is right here. Our total heat load is 16,338, all right? Our total cooling load is 11,762, and this is BTUs per hour, okay? So we need to size a furnace that's going to meet that load, and we need to size an air conditioner that's going to meet that load. Now, unfortunately, the air conditioner is not that simple. There's actually two kinds of load. There's the sensible load here, the total sensible load, and that's just the sensible load up here, plus any ventilation and blower load, just happens to be the same. Those are zeros, okay? And sensible load is the load that changes the temperature of the air. And that's what most people think about. Well, an air conditioner, before it can change the temperature of the air, it also has to dry the air. It has to remove moisture from the air. And if you live in a very humid climate, that can be a significant portion of the cooling. And so the moisture is this number down here, latent. So sensible is what cools the air, changes the temperature. Latent is what dries the air. All right, and we have to pick an air conditioner that meets both of those, not just the total, but it meets both of those, okay? All right, so we're gonna have to pick an air conditioner that meets that sensible load and meets that latent load. And I'll show you what I mean by that in just a few minutes when we come to a break. I have a little diagram that kind of explains that a little bit better, okay? All right, so the next thing we talked a little bit about this yesterday is that you want to double check these. Before you actually pick your equipment, you want to be really, really comfortable with these numbers, because selecting equipment can be a pretty tedious process, and you don't want to go through that process and then find out you made a little mistake. Like I did yesterday, I forgot to put all the people in there, okay? But if you follow those step-by-step instructions, that'll kind of walk you through the process. All right, so the best way to double check these numbers is to come up here to this little button that says reports and just look at some of these reports. So here's a summary sizing calculation. It has these pretty cool little pie charts here. It kind of shows you where all the heat transfer is coming from, okay? And you can kind of look and say, wow, look at windows, interior latent load, that's people, internal gains, walls, infiltration, okay? And if you see anything on here that really jumps out, you go, whoa, why are walls you know, if you look on here and walls are like 2/3 of your heat loss, you say, all right, what's going on there? And then you go back and you look at your walls, and maybe you typed them in as R0 or something like that. You picked the wrong one. So come through here, double check all this stuff. This is a good one to check. Another good one to check on the reports are the by room calculations. So the summer by zones and rooms will show you. So this is the kitchen. So you see it says room number 1 kitchen. So this is all the calculations that Manual J does for just that one room, for the kitchen. It looks at the windows, it looks at the walls, it looks at the doors, it looks at the ceiling, the floors, the infiltration, the internal gains, and the duct load in just the kitchen to get this number right here, this 4463. All right. And then it does the same thing for the bedroom. Go to the next page. The bedroom is 1322. The living room is, go to the next page, 2788, and so on. So those all get added up. And this is a good one to come look too, because this is where you can kind of look at stuff and say, all right, why does that number seem so high? And I thought I had more windows in this room, and there's only one. And you go back and look at your drawing. You go, oh no, that's right, there's only one. All right. So this is a good place to come and look. You know, we have no occupants in this room, so there's no occupant load. So it's just get used to scanning through these things. Also remember I said that what the software does is it takes our drawing, it takes all those walls, it looks at the type. So we defined a wood frame exterior wall with a certain sheathing insulation, and you go to Manual J, you find a table, and the table is this number here. It's called a heat transfer multiplier, and you multiply that times the area, and this is the BTUs per hour associated with that one particular wall. Okay, let me go back. I was talking about the windows, and these heat transfer multipliers are based on orientation. And so this is where you'll see that, you know, for a west-facing window, this will be a really high number, and for a north-facing window, it won't be nearly as high. And that's how Manual J accounts for the different orientations of windows. Okay, and so all this stuff gets added up. And I think I mentioned early yesterday, when I first started doing load calculations back in 1988, there wasn't even software to do this. See this table here? This was a handwritten worksheet that you had to fill out by hand. You had to manually write all these numbers in, do the math, add it all up to the room. You had to do that for each and every room. And then your boss would come in and say, how would it be if we put lowy windows on there? And you're like, ah, crap. And you had to go back and you had to erase all the windows, and you had to change the heat transfer multiplier. You had to re-add everything up, and you know, you just photocopy and start over basically. But that was the old days. Now we got this pretty slick software. And what I like to tell people about software is software helps you make bigger mistakes faster. Okay, so be careful with software. Don't assume it's right. Always go back and double check your work. All right. Okay. So once we're comfortable with these numbers, we're going to have to pick an air conditioner to help us do that, and a furnace. So this next button here says continue to manual S equipment selection.
Someone was asking before, how do you get 1,200 BTUs and internal gains option?
The 1,200 BTUs for internal gains, that was in our libraries, in our room types. One of the room types was defined as a kitchen, and in that kitchen room type is where you specify the internal gains. And 1,200 is a very common number. That's what Manual J recommends for kitchens. You can change that number if you want to, but it's the generally used number to account for maybe having a stove going, or a microwave, or the refrigerator, or something like that. You don't add those all up. You don't say, you know, what if I had my stove going full blast? What if I had my oven going full blast? What if I had the refrigerator running? What if I had the microwave running, and a toaster and a blender, and I had all those running when my air conditioner was running? You don't want to do that for, you know, that bad of a case. And so 1,200 is kind of an average number, I guess you'd say, but it's pretty common. If you change that number, just have a good reason, have a good backup for why you change that number. Okay. All right. So here's the manual S. If this house had more than one system, there'd be more than one of these blue boxes here. It says edit block 1. It would say edit block 2, edit block 3. They would come across here. Okay, but this is, again, this is a very simple house, and so we're just gonna have to do one of them. Notice that there's two steps here. Step one says determine heating and cooling loads, which we've done. That was what we just looked at. So our heating load is 16,000. Our cooling load is 11,007. Okay. Then it kind of has it defines our system types here. This is stuff we put in earlier. Now, when I click on this edit block 1, it's going to open up this little screen here. Go down. And we've got some more steps here. So we got step 1, manual J loads. Step 2 is the AHRI heating and cooling equipment. Step 3 is the AHRI capacities. Step 4 is the fan specifications. Step 5 is estimate the airflow temperatures entering the equipment. Step 6 is your OEM, the original equipment manufacturer specs or design conditions. And then there's a print manual S report down at the bottom. So these steps are basically the process you go through to select your equipment. And this is how Energy Gauge has organized it for you. So up here is our manual J loads. We've got our outdoor conditions, we've got our indoor conditions, and our loads. And then Manual S provides some guidelines for oversizing and undersizing equipment, okay? For air conditioning, it is acceptable to size your air conditioner down to as low as 90% of your load. So you're actually undersizing your air conditioner by 10%, okay? And that is acceptable. But what they're saying is don't go below 90%, okay? Most people, and I personally will use my personal target is 100% because it's hard to explain to a homeowner why you undersize their air conditioner, but it is an acceptable practice, okay? And then as far as oversizing goes, you can oversize by as much as 115% or 15% oversizing if it's a single speed condenser. If it's a 2-speed, you can go up to 120%. If it's a variable speed, you can go up to 130%. That is a ACCA Manual S standards, the ANSI approved standards for following Manual S, okay? If you're just designing for your own purposes, for your own benefit, you don't have to follow these, but these are defensible. If you ever get in trouble, you can always come back and say, hey, I followed Manual S. I didn't go more than a certain percent. And I mentioned this yesterday, and I'll say it again because a lot of people don't realize this. Oversizing air conditioner can cause as many, if not more, problems than undersizing. And I've seen it thousands of times. That you go into a house and they're like, my air conditioner is too small, I'm not comfortable, it's not working. And it turns out that the problem is that the air conditioner is actually too big, okay? And usually the problem is the air conditioner is too big and the ducts are too small. So oversizing is a big deal, and Manual S says don't do it, all right? So, and these are your basic criteria. I've seen these used in a court of law many times, well, not many times, but several times, where, the contractor's trying to defend their design, and they come back and they do load counts after they get in trouble. They come back and they try, and then they're like, oh shoot, man, I way oversized that house, and then they start playing with their loads, try to get it down below these targets here. So just be aware of that. Now, heating for a furnace is not that big of a deal. You never want to undersize a furnace because the building code says you have to provide a heating system that will meet the loads of the house. That's in the building code. That's considered a health and safety issue. And so that's why the minimum says 100%. The maximum, there is some oversizing criteria, and it's pretty generous. You can go up to 140% oversizing if you need to, okay? And then there's a 200% oversizing, the larger furnace only way of saying necessary blower power. Because furnaces aren't just your heater, they're also your fan for your air conditioning system, and sometimes your air conditioning system needs a lot of air. And if a manufacturer doesn't make a certain furnace with a certain size fan that has a low enough heating capacity, what happens is when you pick that fan to provide enough airflow, you're actually picking too big of a furnace in terms of heating capacity. And so ACCA is saying that's okay. You can go up to 200% oversizing if you need a bigger furnace in order to provide airflow. Okay, and I'll kind of do a little demonstration of that. Okay, so that's sort of our targets. That's what we're looking for. So the next step here, and I kind of think this is a little bit out of order. I would rather see this step later on, because now they're asking you for AHRI specific information. And AHRI is the organization that tests equipment. And so when you want to go and provide, real official efficiencies and capacities, you go to AHRI, you find that match, furnace condenser coil match, and then it has an AHRI number associated with it. You can print out a little certificate, and it shows all the, the pertinent information. And that's what they're asking for here. But I usually don't do this at the beginning because I don't know it yet. I have not picked an equipment yet. And as I mentioned yesterday, most of my career, I was doing generic designs that were going to be used to go out to bid. And so I never put this stuff in here. I would let the contractor who's going to actually install the equipment, they would decide. I would provide them sort of design criteria to help them go pick a piece of equipment. But if I were designing, if I was an HVAC contractor doing this design, and let's say I had a special deal with Goodman or Carrier or Train or whoever, and that was the equipment that I always used, then I would be very good at this. I would come in and I'd say, oh, my sensible load is this, my latent load is this. I think that's about it's a really, really small house. But let's just say, use an imaginary number and say, oh, this is about a 3-ton system. And I could go in here and I could fill in, all the information about that 3-ton system. I probably have it all written down, hanging on the wall and stuff, where I can just grab it easily and put all this information in here. Okay, but I'm going to skip this right now. But I think I'm just going to put in some numbers as a placeholder here, and then I'm going to go to this next one, and then this is where it's asking for, all right, for those AHRI test conditions, what is the capacity of that equipment at test conditions? This is just bookkeeping stuff right here, okay? The only time that this stuff is really important for the AHRI stuff is if it's required by code, sometimes for new construction, if it's required for a rebate program, if it's required for, certain kinds of programs and stuff like that. But this is really just kind of bookkeeping stuff at this point. The real important stuff happens in the next step, fan specifications, okay? So we've got some things to enter here. There's a choice of fan types. So you got your constant PSC, your old style PSC motors, or your more variable speed ECM motors. This is a fairly basic intermediate class, so I'm going to stick simple. When you get into variable speed motors, that's a bit more complex topic, which we don't really have time to do. But so take my word on it. We'll just keep it simple for now. And there, oh, by the way, there's some really, really good information online. There's some great YouTube videos. There's some great websites. We actually have a users group, a Facebook users group that you can go and ask questions about Quick Model and stuff like that. So there's a lot of really, really good resources. So if it seems like I'm kind of glossing over something, don't worry. I put my email in there, send me an email, and I'll send you links to more information. It's just, we're kind of limited on time, and I have a bad habit of talking too much. So, all right, so the next thing we want is the fan speeds. This isn't huge. Again, this is just kind of a bookkeeping thing, but typically on a constant speed furnace, it will run on a high speed for cooling and then something lower than that for heating, okay? So on the cooling, you want to make sure you put high speed. On heating, it honestly doesn't really matter. This just shows up in a report, so I'm just going to say medium for now. But what you'll do is you'll look on a furnace table and you'll get that information for what is it on high speed at a certain static pressure, okay? So let me do that real quick. I'm going to pull up a furnace table here. Let's see, fictitious furnace. This is actually something that was used in some old ACA training I used to do. And they actually made up, they called Fictitious American Furnace, OEM performance data. So this is fairly typical. If you were to you know, if you had a make and model number of a furnace and you were to Google it and find the performance data, it's usually a PDF file, and it's going to be many, many pages, and you find there's going to be a table. It goes by different names, the blower capacity table, the static pressure table, the airflow table. But what it is, it's a table that shows the different speeds. So here's high, medium, medium, low, and low. And remember I said on cooling, it usually runs on high speed. And it's going to show airflow. So these numbers across here, if you can see my cursor, these numbers across here are CFMs. This top one, so we got blower speed this way. By the way, these are models. So that's one furnace. That's the 45,000 BTU furnace. That's the 70,000, and that's a 90,000. Okay, so those are three different models or sizes of furnace. You've got your blower speeds here, and then you've got your static pressure across here. What this is how much pressure is the fan working against? The duct system is going to create resistance, and that fan has to blow that air against that resistance. The higher that resistance goes, the less airflow is going to come out of that furnace. Okay, it's like closing a valve or closing a damper. That pressure goes up and the airflow goes down. And that's reflected right here in this table, okay? So a really common number to use is 0.5, half-inch static pressure. This highlighter going here. That's a, shoot. Sorry about that. My cursor's too big. It's not being cooperative here. Let me try the pen. Nope. Okay, so let me zoom in a little bit here. There we go. So a really common number to use is 0.5, okay? And what that is saying is that at 0.5, and this is inches of water column, that's a unit of pressure, at a resistance of 0.5, this furnace is going to deliver 1,128 CFM, okay? If that pressure goes up to 0.6, the airflow goes down from 1128 to 1044, okay? So this is, for this particular furnace, how much airflow is delivered at a certain pressure. And you pick your airflow based on the size of your condenser, all right? And your condenser is going to say, in order to deliver this much cooling, I need a certain amount of, okay? So it's all sort of interrelated, and you know, this manual S is an entire day class all by itself. I've literally taught full day class just on manual S, and we are limited on time, so I'm just gonna tell you, do a little research, take an advanced manual S class, but the important numbers are the furnace, the airflow, the static pressure, okay? We need to figure out what that is. And then the other thing is, I have an actual table, and I'm not promoting any particular brand. If you happen to see the model, oh, there it is. That's a Goodman. I just know how to read Goodman tables, and so I just picked a Goodman air conditioner. This is what's called an expanded data table for a Goodman air conditioner. This is their 1.5 ton. Okay. What I want to show you here, there's a ton of numbers on here, but you can really condense this down to just a few important numbers. So you've got IDV, that's your indoor dry bulb. So that's your indoor thermostat setting. That's a 70, which our indoor, if you recall, was 75. Okay, so we're actually going to use this table down below. Let me shrink this down so we can see the 75. Okay. The other important number is outdoor ambient. That's your outdoor design conditions, okay? And they give you these 5-degree increments. So in Las Vegas, it's like 115, so we'd use this table. In Sacramento, it's about 98, I think, 95, 98. We use whatever table. And if you're in between these tables, you have to interpolate. So you got 95 and 105, so if your design temperature is 100, you're going to have to interpolate. You'll average between these two tables, okay? Let's keep it easy, and let's just say the outdoor design temperature is 95. So we've got indoor 75, outdoor 95. That comes straight from our load calcs. Then we need to know the indoor wet bulb, the indoor wet bulb. And the wet bulb takes into account humidity. And a very common number to use is 63, okay? And if you look down here on this table, you'll see these numbers are highlighted down here with a gray highlighter. And if you go down to the notes, it says shaded area reflects the ACA conditions, okay? And so that's a good indication that that's kind of a good starting point. If you don't know any better, you could start there. But 63 is a common number. For many, many years, I used 65, which meant I had to interpolate between 63 and 67. 65 represents a 50-degree indoor humidity, 50% relative humidity. But 63 is fine. Just use 63. That's good. And so we've got outdoor, indoor dry bulb, indoor wet bulb. Okay. Then we've got airflow. And so here is 676, here is 601, and here is 526. When in doubt, just start in the middle, all right? And so this is a 1.5 ton system. A good starting point, if you don't know any better, a good starting point to start your design is 400 CFM per ton. So 1.5 times 400 is 600, and 601, that's pretty darn close. So that's a decent place to start. So what I typically do is I just start with some kind of generic numbers. I go through the process, and then I come back and I refine those numbers. I fine tune those numbers to what I really think it's going to be. And what you find is these don't change a whole lot. So sometimes your first pass through is pretty darn good. All right, so we've got 75 indoor, 95 outdoor, 63, and 600 CFM. So we can come right along here, and let me explain these columns first. So we got MBH, which is mega BTUs per hour. We got S/T, that's our sensible total ratio. We got our delta T, kilowatts, amps, all this other stuff. The most important number we need at this point is the MBH. That's the sensible, actually that's the total. That is the total. Okay, so 16.7. And so 16,700. So if you remember, our load was like 11,000. So we're good on that. But we do have to check the sensible total ratio. We'll have to calculate that. Let me double check something. It has the TXV on it. That's good. Design subcooling is on there. Dry bulb. Okay. So what I want to kind of show you right here is what impact do those numbers we talked about, the indoor wet bulb, indoor dry bulb, outdoor dry bulb, and airflow have on this number, okay? So if we go hotter outside, so right now we're at 95, let's go hotter outside. Let's go from 95 up to 105. So if we go from right here, 16.7, we go to the 105, look what happens to the cooling capacity. It goes down. That makes sense, right? The hotter it is outside, the harder that air conditioner has to work. So we're going from 16.7 down to 15.8. What if we go cooler inside the house? If we go from 75 down to 70, if we set our set point down to 70 inside, and the air conditioner is having to deal with trying to cool 70-degree air, we go from here to here. Oops, sorry, nope, too many. That one right there. Okay, 16.5. That's not that big of a drop, is it? 16.7 down to 16.5 is not that big of a drop, but look what happens to the sensible total. The sensible ratio changes. We went from 76% sensible down to 62. All right, so something happens there. It is a good time right now. Let me just finish kind of a couple points on here really quick. So we talked about making it hotter outside. We talked about making it outside. Now, what I didn't mention, when you make it cooler inside, remember our load calc was based on that number, 75. And if we suddenly say, well, we want it to be 70 inside, that changes the delta T. We'd have to go back to our load calcs and change the indoor temperature to 70. And then guess what? Our delta T changes, our loads go way, way higher because we've reduced the indoor temperature by 5 degrees. So you don't want to do that. But I just wanted to illustrate what happens. The other thing that's important to understand is these little numbers up here, your entering wet bulb temperature. So if you go from 63 wet bulb and you make it more humid inside, where am I here? Mega BTUs, 63. It goes this direction. It changes that. So it changes your cooling capacity of your equipment. So what it's putting out changes depending on the indoor humidity, the outdoor dry bulb temperature, and then the last thing I want to show you really quick is airflow. So what if we go, instead of 601, what if we go, let's go lower, because that's usually what happens. You undersize the ducts. So we want 600 CFM in order to get this number up here, or we're hoping to get that number. What if we undersize the ducts, and instead of getting 601, we get 526? We will be there, 15.4. That's a pretty substantial drop. So reducing airflow reduces cooling capacity, increasing outdoor temperature reduces capacity, increasing humidity reduces capacity, and I think I already said airflow, and the indoor temperature, design temperature. All right, so just letting you know that all those things and affect this number. I know I'm just kind of throwing a bunch of stuff at you, but it's important to understand that, first of all, one of the most important numbers is this one here, airflow. So if you want to ensure that you're going to get the right amount of cooling out of your air conditioner, you have to make sure you design your ducts for a certain airflow. And the way to do that is, I'll go back to my furnace. This guy is by sizing our ducts to the static pressure. Remember I had said on high speed at 0.5 we get this much CFM, and I'm sorry I don't have the right table for the example we were just doing where it was 600 CFM, but the same sort of thing happens. You have 0.5, you look for a number around here that's around 600 CFM, just knowing if you go more resistance, the airflow goes down. So this number right here, whether it's 0.5 or 0.6 or something in between, we want to design our ducts to that number. That number becomes an important design criteria. So the pressure and the airflow, okay? So let me go back now to energy gauge. Yep. So I'm going to put some numbers in here. I'm just going to throw in, this is a little tiny system. Let's say we went through the manual S calculation. We picked a 1.5 ton system, and we're going to put, say, 500 CFM on heating, and we're going to put 600 CFM on cooling. I'm going to put 601 here, because remember, that's what that table said. I just want to be able to recognize this number when we see it somewhere else. And let's say that was at 0.5 and, oops, 0.5, type. Okay, so by telling the software we want 601 CFM at 0.5 inch static pressure, that's going to go back to quick model when we do our manual D calculations. That becomes a very important number for manual D. Down here, I'm going to click on this next one real quick, and this is just suggestions for what your indoor dry bulb and wet bulb, your air, entering air cooling coil. So this is the temperature of the air that's going back over the coil. It'll calculate these for you, and what it does is it adjusts the numbers a little bit based on duct gains and stuff like that. Not a huge deal. And then we can type in those numbers that we got from those tables, okay, and type those in here. This is our design conditions, so we can say. So I'm just going to take a first pass through this. I think it'll let me go back here. save work and return to quick model. And so if you remember that 601 that I typed in, and we'll go to our rooms. And let me show you. So this is our room table that we looked at before. So it's got our rooms named, our zones, our floor areas, our volume, the type of room, the number of people. Now from this line over, this is all from energy gauge. This is all from manual J that we just typed in there. So these are the room by room heating loads. These are the room by room cooling loads. Here's our total. These numbers should look familiar. 16,338 and 10617. That's a little different. Something must have changed. But that was our heating load. It went down a little bit for some reason. 11,617. But anyways, that came back. Okay. And remember I said that there's a percentage. If this room is 10% of the total, it means 10% of the air. We call that the fraction, the heating fraction and the cooling fraction. So this number here is the heating load for the kitchen, and this is its fraction. 0.269 is 26.9% of the total load. All that is this number divided by the total, and that's a percent. This room percent is 21%, this one's 30%, this one's 16.7, this one's 4.8%. You add those up, it gets to 1. Okay, let me go over here to the cooling. So here's our cooling loads, here's our cooling fraction. Here's that 601 CFM that I typed in at a certain static pressure. 601 is the total cooling airflow. And if you take this number was 47, this room is 44.7% of the total. Therefore, it needs 44.7% of the air. If you multiply this number times 601, you get this number right here. So now these fractions that are based on whatever percent total of the cooling load is, these fractions are multiplied times the 601, and the air is distributed proportional to that room's load. So if this room's load is 11.8%, the airflow is 11.8%. This 71 is 11.8% of the 601. So now that airflow, I call it the fair share of air. If it's 10% of the load, it gets 10% of the air. That's what's going on here. So the software is doing all those calculations for you. So it did the room by room load counts. When we looked at those reports and it had all those rooms totaled up, that's where these come from. We saw those totals. We entered this number. We entered a 0.5 inch static pressure. I'll show you where that comes up. And so now this is how much air we need to get to each room in order for that house to have balance. And balance means the room is getting its fair share of the air. Okay? One of the sayings I like is don't waste time splitting hairs when your job is to shave heads. Okay? You need to get through this quickly. You need to take your best guess and move on. I have literally seen people freeze up and stop doing a load calculation because the software was asking them, is this wall light, medium, or dark? And they're like, I don't know. It's a medium gray. Is it medium? Maybe it's dark. Maybe it's light. I don't know. And they freeze up. Just move, press on, move ahead. Take your best guess. Make sure it's defensible. And then when you're doing this early on, the other thing you're going to have to do, I have the advantage of literally having done thousands and thousands and thousands of load calculations. Okay, so I have that advantage. I know what's important. I know what's not important. Until you have several hundred load calculations under your belt, what you need to do is, if you're not sure about something, like people, is run the loads, go back, change that one variable, run the loads again, and see how big of a difference it makes. And you're going to have to do that over and over and over again until you're comfortable, until you have a good understanding, a good fundamental understanding of what's important and what's not. The other thing is, if you have an actual hard copy of Manual J, you can open up a table and you can look at the table and see what's happening when you pick a light wall versus a medium wall versus a dark wall, and just go and looking and say, well, that multiplier hardly changes at all. Why should I even worry about it? Okay. But of course, the easiest way to do is just change it in the software, run it, write down the number, change it, run it, and see how big of a difference it makes. Okay. So I really, really encourage you to do that frequently until you get comfortable knowing what's important and what's not. So let's go ahead and start back up. This is something I was trying to find earlier. I said I'd do it after the break. Remember I was mentioning sensible load and latent load, okay? And your house has two loads, sensible and latent, and the equipment has two capacities, sensible and latent, okay? And you need to pick your equipment so that you make sure it meets both of those, sensible and latent, okay? And what I mean by that is illustrated fairly well in these two little charts here. So the one on the left, this is the load of the house. If you can read this small print down here where my cursor is, it says load of the house for a humid climate, all right? So in a humid climate, you might have this much sensible load and this much latent load, okay? And that's a fairly big percent of the total because we're in a humid climate. Over here, we have just sort of a relative comparison of the same house in a dry climate. And the main difference is that the latent load is proportionally smaller. So this is a dry climate. You got a lot of sensible, a little bit of latent. This is representative of California. And over here, you've got a lot of sensible, but also a lot of latent. So this would be like Florida or something, okay? Now, next to it, we have two different air conditioners, two different size air conditioners. Let's say a 3-ton and a 3.5 ton, okay? Air conditioners have two kinds of capacity, sensible and latent. So that relationship, that ratio between those two depends on a variety of things, okay? But primarily just kind of how the air conditioner is built. And so this air conditioner, whatever size it is, has this much sensible capacity and this much latent capacity. And so you want to pick an air conditioner, whether it's this one or the next size bigger, to make sure that it meets both of these. So you have to look at sensible, and you can scan across here and say, okay, this sensible capacity is bigger than the load. So this works right here, the sensible works, but now let's check the latent. And the latent is here, and the latent load is bigger than the capacity, so it doesn't have enough latent capacity. So we go to the next size piece of equipment, the sensible is good, and the latent is good. So this is the piece of equipment that you're going to want to pick. So that's an extra step that you have to do in a humid climate as opposed to California or a dry climate. We look at, here's our sensible and our latent load. We look and we measure our sensible, and that looks good. And our latent is also good, okay? Because this relationship is fairly stable on capacity, but in a dry climate, this latent load is usually really, really small compared to this. And 99% of the time in a dry climate, when you pick an air conditioner that meets the sensible load, it will also meet the latent load. So it's one less step we have to deal with in California when we do our manual S calculation or you know, any dry climate. I did a lot of design in Las Vegas, and your latent load is like teeny tiny. It's like this little barely visible, thank you, little latent load. So you don't even have to worry about latent load. In fact, Las Vegas, I think, has a negative latent load. Moisture is absorbed into the Ethernet there. So that just kind of explains, you know, sizing your equipment for latent and sensible. Okay, let's go back. So to kind of review where we were right before the break, we went in, we did a very crude, rough manual S, and I apologize, I can't go into a whole lot of detail on that. We just don't have time. But the important thing was we had an airflow and a static pressure from the furnace, and we needed to ensure that we got that airflow, that 601 right here, 601, because if that number goes down, our capacity goes down and our air conditioner may not work as well and it may not perform like we want it, okay? So we're going to size our ducts to ensure that we get this, at least this 601. And as I mentioned, it's a bit more complicated if you have a variable speed furnace. Variable speed furnaces will adjust, okay? But you have to pick a starting point. Even with the variable speed furnace, you have to pick a starting point and sort of do a similar type of sizing criteria. But this is a more simple constant speed furnace on this little bitty house, okay? So we want to ensure we're getting the 601. The other thing we want to do is make sure that 601 CFM goes to each room proportional to its load, and that was all these calculations up here. So as long as we can get at least 268 to this room, 75 to this room, 164, 71, et cetera, then, and at least a total of 601, we can be comfortable, we can be confident that that house is going to be within a relatively even temperature throughout. Now, if we go way too high, you can have too much airflow in a room as well, okay? If we oversize a duct going to a room, and let's say the kitchen here, and let's pick another, let's pick bedroom 1. Bedroom 1 only needs 75 CFM, okay? What if we did something silly, like assume there's 4 bull mastiff dogs playing in that bedroom, and this load went way up, and this cooling fraction went from 12.4 to 24, so it doubled, and this CFM went to 150, okay, we would put a much larger duct to make sure we got 150 CFM in that room. Now, the problem is when those 4 dogs aren't in that room playing, we've got way too much air going to that room, and that room is going to get cold, okay? So you can oversize the duct. The other thing, too, is, and this is just one of those nuances of duct design, is where are you going to put your thermostat, too? Because the thermostat is going to sense the air that's passing it, not the air in the rest of the house is going to sense the air passing it. What air is going past the thermostat? Okay, we'll talk about that in a little bit. But, all right, so we want to ensure the 601. In order to ensure the 601, we have to make sure that the resistance of the duct system is not more than ½ inch static pressure, okay? So now we're getting into manual D duct sizing. So there's this button up here, and we just make sure we're also following our step-by-step instructions. Before I get ahead of myself. We got our loads. We are on J. Go to the rooms table, data tab, confirm that the room loads and airflow look reasonable. So that's these up here. So we got our 601, this is our 500. Oh, by the way, I forgot to mention this too. This final last column over here. So remember, we're sizing ducts for 2 situations, heating mode and cooling mode. Heating mode, the airflow is generally less than in cooling mode. So we got 500 here, we got 601 in cooling. And the distribution of the air in heating mode is based on the heating load, okay? And what occasionally happens is even though the total is less, sometimes a room, because of the side of the house that it's on and other things like that, sometimes the heating load airflow is higher than the cooling load airflow. And if that's the case, you want to make sure that the duct will accommodate the higher of those 2 loads. So what the software does for you is it scans down the cooling CFM and it scans down the heating CFM and it picks the higher of the 2. So if we look here, we got 268. Here we go. The cooling CFM in this room is 75, but the heating CFM is 106. So we want to size the duct to that 106. So what happens is we create a new column, and this new column is called Duct Size Cfm, and all it is, it's the higher of these 2 columns, heating and cooling CFM. So that one's different, and that one's different, and that one's different by 1 CFM, okay? So we're actually going to size our duct system to 646 CFM instead of 601. And that's because a few of the ducts need a little extra CFM because of the heating system, okay? Now, I'll just kind of forewarn you and say that may or may not change the duct sizes. When you start sizing ducts, as we'll see in a second, is you're going to round up to the next duct size, and sometimes that gives you a lot of extra capacity, and sometimes it's enough to handle the difference between the heating and cooling airflows, okay? So that'll make more sense when we get to that point, okay? So these are the actual CFMs we're going to size each duct to in each room, okay? But before we do that, we have to do something called a friction rate. And friction rate is best described as the amount of pressure that's lost as the air travels down the duct. So remember, we have that half-inch static pressure. Think of that as our bank account, okay? We have half-inch static pressure. As we go down the ducts, we're going to lose money from our bank account. And the rate at which we lose money is how much we have is our budget, okay? And our budget is going to depend on how big or how small the duct is. And if we want to have money left when we get to the end of the duct, we need to make sure that duct is a certain size. And friction rate is the number describes how much money or static pressure you're losing as you go down the ducts. Okay, that's the best I can do on short notice. I actually wrote a really long, involved blog article. So if you go to my blog, russellking.me, there's an article, I think it's the most recent one, called Friction Rate Explained, maybe, okay? Because I even get it messed up. Every time I mess around with friction rate, I always have to stop and remind myself, is bigger ducts or smaller friction rate? You know, I just have to remind myself. So it's not an easy concept to understand. All right, so we go to friction rate. Actually, our step-by-step instructions is telling us to start drawing ducts. Let's go ahead and do that. That's actually more fun. We'll get to friction rate in just a minute.